We have a partial of that function with respect to x, okay, which is the slope of the tangent line that's produced when we take this surface and intersect it with a plane parallel to the x-axis containing the point in question. So if I have a surface and a point, and I want the partial with respect to x, take a plane that's parallel to the x-axis that contains that point. The intersection of that plane with the surface will produce a curve. The slope of the tangent line to that curve at that point is the partial derivative of that function with respect to x. And you find it by taking the derivative of the function holding y constant. Now, if you want to find the partial with respect to y, you've got your surface. You intersect it with a plane parallel to the y-axis. At the point in question, it'll give you a curve. The slope of the tangent line to that curve at that point is the partial derivative with respect to y. Okay, we have that. Then what did we talk about? We talked about a gradient. The gradient is a vector in 2 space, in the plane, x, in the xy plane, that points in the direction of maximum change of that function. Okay? Maximum change. Every surface at a point will have an infinite number of tangent lines. Infinite number of tangent lines. Some will have positive slope for going this direction. Some will have negative slope. Some will have 0 slope, going this way or this way, 0 slope. They'll have an infinite number of tangent lines. The set of which, if you take all those tangent lines, will describe a tangent plane. Okay? It would describe a tangent plane. The gradient is that vector in 2 space that points in the direction of the maximum slope of that tangent line, the maximum tangent line. Okay? The greatest ascent. Right? It'll point in that direction. Okay? The direction of greatest ascent. Not only that, but the magnitude of the gradient will give you the maximum slope of all those tangent lines. It is equal to that maximum slope. Now, what about those other tangent lines? Well, those are all directional derivatives. In other words, we've got a surface here, and we've got a point. Not only do we have the intersection of that surface with a plane parallel to the x-axis and parallel to the y-axis, we have the intersection of that surface with every plane in perpendicular to the xy plane in every direction. And every time we intersect it with a plane, no matter what, I'm not blessing you guys, I'm just, these are the directions, okay?
I'm so almost.
Need it. Yes, my son. All right. Every time we intersect it with a plane, we're going to get a curve. That curve will have slopes of a tangent line. So we have the slope of the tangent line in that direction, in that direction, in that direction, back the other direction. We have an infinite number of these slopes of tangents. Each one is a directional derivative. Now, how do we find a directional derivative? Here's what we're going to do. We're going to say, okay, let's find the derivative in a direction that's determined by a unit vector in the xy plane. So we're going to take a vector in the xy plane and make a unit vector on it. That unit vector will have the components cosine theta, sine theta. Okay? If you have a unit vector, I don't have the plastic camera, but if you have a unit vector in the xy plane, its x component will be cosine, its y component will be the sine of the angle. Okay? But is that reasonable? A unit vector? In the xy plane, I can do it on the board.
Yeah, I like pictorial representations of these abstract thoughts.
Yeah, well,
Well, I mean, really now.
Here, let me just mention this. That if you have a unit vector in the xy plane with an angle theta, so this is length 1, the x component here will be cosine theta. Okay? Because what's cosine theta? Cosine theta, okay, is equal to the adjacent side over the hypotenuse. Well, the hypotenuse is 1. So what is cosine theta? It's the adjacent side. It's the x component, okay, of this vector. Now, what about the y component of this vector? That's the y component. What's that equal to? Well, the sine of theta is the opposite over the hypotenuse. It's the opposite side, which is our y component of this vector. So what I'm saying is a unit vector, any unit vector in the xy plane can be represented this way, cosine theta, sine theta. Suppose it's the unit vector along the x-axis. That's the I vector. What's it equal to? Well, the angle is 0. It's equal to cosine of 0, 1, sine of 0, 0. It's equal to 1, 0. That's the unit vector along the x-axis. What's the unit vector along the y-axis? Well, the angle's pi over 2. What's the cosine of pi over 2? 0, and the sine of pi over 2 is 1. That would be the vector 0, 1, the j vector, okay? Okay, so any unit vector in the xy plane can be represented this way. So here's what we're going to do. Is it okay if I move around? No?
I'll just have to keep moving around.
Oh, I'm sorry. Here, let me stay here.
You should get multiple cameras.
Either that or get multiple burns.
I just feel awkward.
Yeah, all right. All right, that's good. All right, but anyhow. In that direction. Our directional, let's start there, along the x-axis. That directional derivative along the x-axis, another name for that directional derivative along the x-axis would be what? What would be another name for the directional derivative along the x-axis? It would be what? No? Well, that's a good shot, though. Another name for it would be a partial derivative with respect to x. Because that's what the partial derivative with respect to x is. It's the directional derivative along the x-axis. It's the slope of that tangent line that's produced by intersecting our surface with a plane parallel to the x-axis. It's the slope of the tangent line in the x direction. That's what a partial derivative is, and that's what the directional derivative is in that direction. Now, what unit vector are we talking about? We're talking about the unit vector 1, 0. Let's move this way. We want a directional derivative now. We're moving off the x-axis and going in this direction. What happens to the cosine of that angle? It's decreasing, and the sine is increasing. Let's go at a 45-degree angle line here. What should our directional derivative be along that 45-degree angle line? Well, it should be equal parts, partial with respect to x and partial with respect to y. After all, it's the one right in between the two, right in the middle of the two. That's what happens with the cosine and the sine of that unit vector. They're the same. And if we get over to this side, we have a partial with respect to y. What unit vector are we talking about? 0, 1. So here's what I'm saying. Directional derivative is equal to, I've got it over, I have to go over here.
Straighten it out. Here, can I sit next to you?
The directional derivative is equal to, well, given a unit vector, cosine sine, and a point, given a surface, that directional derivative in the direction of u of our function at that point is equal to a dot product of our gradient times the unit vector. The gradient, we call the gradient, partial with respect to x, partial with respect to y. Partial with respect to x times cosine plus partial with respect to y times sine. And hopefully this makes some sense. If we start with the partial with respect to x, in that direction, directional derivative in the direction of the x-axis, the cosine is 1, the sine is 0, so it's partial with respect to x. As we move in this direction, heading towards the y-axis, this is decreasing, this is increasing. When we get to the y-axis, the cosine is going to be 0, and the sine's 1, and it's all partial with respect to y. Directional derivative along the y-axis, another name for it, partial with respect to y. Okay? And if you continue around 360 degrees 2 pi radians, that's what you do. What the directional derivative is parts of sine and cosine depending on where we are, how close we are to the x-axis or y-axis. What do you think? Let's do an example. Let's do some examples. I can show you. All right, so what we're going to do This is all what I just said here. Okay, let's define our function. Let's take our paraboloid, z equals x squared plus y squared, in a point 2, 1, 5. Okay, so we're going to do this. Here's our paraboloid here. Okay, and there's a point, 2, 1, 5. Okay, that black thing right there is our point.
That boil?
Yeah, this thing here. Yeah, whatever. All right? That's how the points look. We're going to tell you. All right? So here's what we're going to do. Let's find the directional derivative in the x direction and the y direction. First, let's do the x direction. Theta equals 0. Okay. Now, there's a trick to twirling this so it doesn't tilt. Okay, here we go. All right, this is the x-axis. I don't know if you can really see that, but that's the x-axis here. So what I did, I took a plane parallel to the x-axis and intersected our surface at this point. That intersection is going to describe a curve. There's the curve right here. You can see it. It's a parabola. Maybe you can even see it better if I twirl it a little bit more. Okay, there's that parabola. The slope of that tangent line right there is the partial derivative of our function with respect to x, and it's our directional derivative along the x-axis. Those two are the same. And what I did down below showed you the vector in red down here.
And
That's going along the x-axis. That's the unit vector going along the x-axis.
Wait, so is that red vector down there the gradient as well?
That red vector down there is not the gradient. It's the unit vector in the direction here. The gradient at this point is going to be a vector down here in that plane, but it's a vector that's going to be pointing in the direction of maximum ascent. It wouldn't be this one. That gradient is going to be 2x, 2y. It's 2x, 2y. Okay, that's the gradient, 2x, 2y. At this point, 2, 1, 5, the gradient at this point is going to be 4. Okay, 2x, x is 2, so 4, 2. The gradient is going to be the vector 4, 2. So at that point, 2, 1, 5. If you want to go in the maximum ascent on this parabola, you will go in the direction of 4, 2, in that direction, right in that direction. Okay? Now, the unit vector that's down there, 4, 2, would be the unit vector 4, 2 divided by the square root of 20, okay, square root of 4 squared plus 2 squared. It would be that unit vector along there. Okay, so if you want to climb this thing in a maximum way, you would head in that direction. And that would bring you up the paraboloid in a maximum way. That's what that would be. All right? All right, I'm going to show you some more. So hopefully it'll get clearer as we go along. Right now. All right, everybody see this okay? Partial with respect to x. Directional derivative along the x-axis. Take a plane right parallel to the x-axis at that point and get this parabola. Okay, you with me? All right, let's do the direction along the y-axis. 0, 1. Theta now is pi over 2. Let's run this. Same point. But now my plane is parallel to the y-axis. And this is the y-axis here now. This is the x-axis. This is the y-axis. It intersects in a parabola, but you'll notice that the intersection now, the parabola, the point is lower, closer to the vertex of the parabola. And the other one, it was up higher. See, here's the vertex here, it was up higher. So this slope is greater than this slope. It's lower down, closer to the vertex. The slope of this one partial derivative is still 2y, but now y is only 1, so the slope of that one is 2. The slope of this one is 4, because x is 2. Derivative is 2x. Partial derivative with respect to x is 2x. Okay? This one here is less steep. Okay? So it's 2. Right here. Half the slope of the other one. All right, I'm going to go in the middle now. Pi over 4. This is a directional derivative in that direction. And let's take a look. Okay. So now, I'm taking my plane midway between the x-axis and y-axis. And again, it's going to describe a parabola. Okay, it's going to describe a parabola, and this is the slope of that tangent line is the directional derivative along that 45-degree angle. Okay, that's what I have right here. All right. Everybody with me on that? Okay, here it is. What is that directional derivative? It's 4 over the square root of 2 plus 2 over the square root of 2. How do you get this? You take the dot product of our unit vector, right here, 1 over the square root of 2, 1 over the square root of 2, with the gradient, which is 2x, 2y, that's our gradient. X is 2, so we get 4, y is equal to 1, 2. So take 4, 2, gradient, dot, unit vector to get this. That's the slope of that tangent line right there. Okay, what I did is took, that's what I said. Okay, this is greater than the other two, but it's not the greatest. Where's the greatest directional derivative? The greatest directional derivative is in the direction of the gradient. Okay? Here you go here. Maximum directional derivative is in the direction of the gradient. Gradient's 2x, 2y, like I've been saying. So here we go. At this point, the gradient is 4, 2. The magnitude of the gradient is 2 square roots of 5, and that's important. Not only is it important to make a unit vector, because directional derivatives need unit vectors, okay, so I'm going to take my vector and make a unit vector, but the magnitude of the gradient is telling me what the maximum slope is. That's going to be 2 square roots of 5. That's the maximum slope of all of the tangent lines to that surface at that point. It's the greatest, okay? This is the maximum directional derivative. All right, and now we're going to do it. Here we go. We're going to do it right here. Yes. This one here is the one that's highest up on that parabola. That's the intersection. It's the greatest of all the directional derivatives. Okay? This one right here. It's in the direction of the gradient. Oh, okay. All right, now I'm going to say, let's find out where the slope of the directional derivative is 0. And what I do, I find the directional derivative at any point and then solve for theta. Okay? And it turns out that theta is going to have to equal the inverse tangent of -2 in order to cause that to be 0. And then I draw it along that, in that direction. So here we go. In that direction, the slope of the tangent line to the curve is equal to 0. Okay? It's at the bottom of that parabola. That's the direction where you have a 0 directional derivative. All right, now what we're going to do, the pièce de résistance, is a manipulate. We got anybody still awake? Who's still awake? Oh, one person. Okay, that's good enough. That's good enough. All right, here we go. I'm going to move this around. Okay, that red arrow is my unit vector in the plane.
What are you
using panel for?
What am I using, what?
The show option panel.
It's not panel, it's plane one.
Oh, okay.
Yeah, that's what it is. This is the plane here. I call it plane one for some reason. Let's change the angle around. As we change the angle, we're changing the directional derivative. And you can see the directional derivative is 0 here, negative here. As I change my direction, negative, 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 back to 0 again, positive, steepest possible positive right there. Okay, as I change it around. And if I continue, if I go back the other way, now what I can do is have Mathematica do this for us. So what I'm doing is changing the direction. And you can see that slope of the tangent line as it goes around the 360 degrees. Okay, those are all directional derivatives. And where's the maximum one? It's in the direction of the gradient. And what is the maximum slope of that tangent line? It's that magnitude of the gradient, 2 square roots of 5. Yes, Liam?
What was that tangent that you showed us that was right before the gradient that you said was greater than the 2 partial derivatives? Wait, was that it?
This one here? This one would be greater because it was in between. It was along the 45-degree angle line. Yeah, then I did the gradient. So that was pretty close to being the maximum, but the maximum turned out to be a little bit different than that because of the point.
Because of 2 and 1.
Yeah, because of the 2-1, exactly, because of the 2-1. But there you go. Now, for some reason, I did another one of these. I don't even know what the other one looks like, but I want to show it to you guys, okay? And I don't even know what it is, since I didn't have a chance to check it out this morning. So let's, okay, I can't see my Dropbox because Mathematica's in the way. Okay, hold on a second. We go to my Dropbox again here. Let's get the second one. I have another one in here. I'm not sure what I did for the second one. Directional derivative number 2. Let's do this one. Not sure what I did here. Okay, there's what I said before. All right, I guess I just did another example. Here's a function, 8 minus x squared. Now, there's no y, so it's a cylindrical surface moving parallel to the y-axis. That's what this is doing. And I've got a point, 1, 0, 7. That's this point. Okay? And I'm showing it here, so let me run this cell. There it is there. Oh, I don't have the image large in this one. There's the point, okay? So, let's do some directional derivatives here. I don't need a palette. Okay, so, slope of the tangent line, this is along the x-axis. Here's the x, so this is the partial derivative with respect to x. Please notice that it's negative. And again, if you were to take the partial derivative of 8 minus x squared, you would certainly get negative 2x. And at this point, okay, and the point is 1, 0, 7, so the slope of that line is going to be a negative 2. That's what the slope of that line is. Okay, now let's do, this is what this is. Now, let's take another point, 2, 1, 5, and find the partial with respect to x at 2, 1, 5. So what the heck? I don't know. Let's just do it. Not that. Let's do this. Okay, at 2, this one is going to give us the 0 slope. Okay, right along here. Let's do this one here. This is along pi over 4. you can see that's also negative. And then I'm going to do at pi. So I do various ones here. No, let's do a manipulate. This is the only one that's worth doing. Okay, as I move the plane around different directions, you'll see again, you've got slopes of tangent lines that are going to be different. Okay? And these things are going to go around and describe that tangent plane to the surface at that point. Positive, positive, 0, negative, pointing downward. It's the same thing as before. Where's the maximum slope? In the direction of the gradient. What is the maximum slope? It's the magnitude of the gradient. Okay? There you go. All right. Phew. I'm working like a dog. Okay, so what you're going to have to do is, let's do this problem. Dave's got a problem there. Let's do that. And let's go back to the document camera. Can I do that all right?
I'll just record it anyways, whatever.
Oh, okay. We'll continue recording. And let's go do this problem. Math team today. Critical math team. This is it. This is the competition today. How you guys feeling? Pretty good?
Who's that guy from the Cowboys that show?
What's that?
Who's that guy from the Cowboys that show?
Their whole team.
Yeah.
No, somebody, what, dropped a pass or something?
I don't remember. I just know I was making choking jokes.
Oh, I don't know. Romo's hurt. He's out. He's not even. All right, so let's take a look at this.
I feel like him.
Burns, still hit record though. Do you have the card there?
Yeah, I have the card.
Yeah,
You
still.
want me to record
Yeah,
from
still
here?
record. Yeah.
That's pretty fun.
Solid. Let's find the gradient of the pen.
The card. Okay, here it is. I'm sorry. It's here. I just don't like yanking it out of here like Windows things. Mac. I did go see the movie Steve Jobs yesterday.
Oh, you know, Macs are much more complicated things. Yeah.
I should have brought a black turtle with jeans. All right, but anyhow, let's do this problem. This is a problem where the function is. Thank you.
Record.
I'm recording it. And today is 11/2/50. X cubed minus y cubed. The point apparently in the plane is 6, 5. Okay, that's a point in the plane. We're given a vector, which is square root of 2 over 2, square root of 2 over 2, which is along a 45-degree angle line. We want to compute the gradient of the function. The gradient of this function is partial with respect to x, partial with respect to y. And we want the gradient at this point 6, 5. So we're going to get 6 squared, 36 times the 3, 36 times 3, 108. And we've got a negative 75. So that's going to be the gradient at that point. So here we have a surface, we have a point in the plane, we have a gradient at that point. What is the gradient? It's a vector in the plane pointing in the direction of maximum change. That vector is 108, okay, negative 75, so it's back that way, okay? So that vector from there is pointing in the direction of maximum change on this surface. Okay, now what do we want to do? We want to find, we've got a unit vector here. Square root of 2 over 2, square root of 2 over 2, that's the same as v.
That's what they gave.
Okay. So we got a unit vector, and what we want to find is the directional derivative, okay, in this direction of this surface at that point. And you find the directional derivative is a unit vector. I should have made a unit vector. What you do is take the dot product of the gradient with the unit vector. That will give you the partial with respect to x times the cosine of the angle, partial with respect to y times the sine of the angle. Okay, that's how you find a directional derivative in any direction. Okay? So, at this particular one, the partial with respect to x we said was 3x squared. The cosine of the angle, this is in a unit vector, the x component is the cosine, the y component is the sine. And the partial with respect to y times the sine of the angle. And now we're given that x is equal to 108. Okay, x is equal to 6. Sorry. 3 times 6 squared, square root of 2 over 2, minus 3 times 5 squared, square root of 2 over 2. And we end up with 36, 18, 54, square root of 2, minus 75 halves, square root of 2. Great Scott. Okay, that's okay. This is 37 and a half. We end up with what? 16.5. We end up with 108 over 2, square root of 2. 75 over 2, square root of 2. 33, square root of 2 over 2. That'll be the slope of the tangent line to that curve, that surface, in that direction, at that point. Put that in. Oh, you don't have it.
Do it later.
What is it?
I have to do it later because I don't have my thing.
Okay. That's what it is. All
What
righty?
is that right there? 33.
33 square root of 2 over 2 is, what is that? That is the slope of the tangent line to this surface, x cubed minus y cubed, at this point, 6, 5, and whatever the point is on the surface, in the direction of that direction, 45-degree angle line from the x-axis, in that direction. So take a plane in that direction, right through Janish, right through his head, right here. Okay? Take this plane, okay? It's going to intersect our surface in a curve. At that point, it's going to contain this point. It's going to be a tangent line. The slope of that tangent line is 33 square roots of 2 over 2. That's what the slope of that tangent line is. That's our directional derivative in that direction.
On the point 6.5.
Yeah, 6.5 is down there. 6.5, 6 cubed is 216, 5 cubed is 120.